All right, guys, we're not really going to extend too much from what we did yesterday, but we're going to start adding, subtracting, multiplying, and we're going to start doing that with binomials that involve imaginary components. If we have a binomial that has an imaginary component, we call it complex. All right, so this is something that we talked about yesterday, but basically if we have something that's of this general form where it's got a real component and an imaginary component, we call it complex. All right, so what we're going to talk about today is how to graph these complex solutions and just how to simplify some of them that are a little confusing. So let's start with just a very basic example in A. I've got a binomial here that is complex and another binomial here that is also complex, and I'm subtracting them. So just like if this were two real binomials, I would stack them. 1 minus 2i minus negative 2 minus 5i. Be careful with your subtraction, right? So if I do negative 2 minus negative 5, I can do keep, change, and that gives me 3i. And then if I do 1 minus negative 2, again, I can do keep, change, and I get 3. So 3 plus 3i is my solution. If I want to graph this, I can put it on a graph here, but this is not the graph you're used to seeing. Usually you'll see an x-axis and a y-axis. That's not true anymore. It's not x and y. We're going to relabel them. This is your real number line, and this is your imaginary number line. That's the only difference here. So we're going to put our real component here, and we're going to put our imaginary component here. All right, so on our real number line, my real number, the real component is 3. I could count by 1, right? So I'll do 1, 2, 3. That's my real number line. Just maximizing my space and using 2 blocks for 1. And then my imaginary number line, I could also count 2 blocks for 1. But my imaginary unit is I, so I have 1i, and then I would have 2i, and then I would have 3i. And if I wanted to go the other direction, I would have negative I, negative 2i, negative 3i, and I could keep going. So now all we're going to do is we're going to plot this component. This is our real component. That's at 3, so that will be here. And then we're going to plot our imaginary component, and that will be at 3i. So where do these two things intersect? Well, they intersect right there. So that is the point. Now when I plot a complex solution, it's important to remember that you should draw a ray from the origin out to that complex solution. All right, so this is how you'll graph a complex solution. And this is not something that's probably going to come up on the Common Core exam. You probably won't have to graph a complex solution, but if you do, you need to remember that there is a point which you can plot on the real and imaginary number line, and then the ray is important. There should be a ray going out to that point. Okay, so the big key here, though, is making sure that you're able to do your subtraction, and we're going to be simplifying some even more complex solutions pretty soon. Like these. These are more like the type of thing that you'll see on unit test or a Common Core exam. We do have some complex solutions here. This is a complex number. I've got a real and an imaginary component. And this is complex. I've got a real and an imaginary component, although this is in bi plus a form, so a little bit different. If I'm squaring something, like I am in C, that means I have 3 plus 4i times itself, so I would rewrite it. Okay? And if I multiply these two things, what I'm going to be doing here is basically foiling first, outside, inside, last. All right, so my first terms, if I multiply them, give me 9. 3 times 4i would be 12i. And then 4i times 3 would be another 12i. And then 4i times 4i is 4i squared. I write it like this to show you that this is the intermediary step that you are getting to before you get to 16i squared. Because if you don't write this step, and I expect that probably in a week you won't be writing this step anymore, you may forget that the I is also squared. It's kind of like an x or any other variable at this point, right? If you do I times I, you get I squared. So I'm going to have 9 plus 24i plus 16i squared. And I'm not done. Because remember our I cycle? Our I cycle says that if I have I, that stays like that. But if I have I squared, it's -1. If I have I to the third, it's -I. If I have I to the fourth, it's 1, and we keep cycling. Well, right now I see an I squared. So I can replace that I squared with a -1, which means what I really have is 9 plus 24I minus 16, because 16 times -1 is -16. And then I can combine these two like terms, and 9 minus 16 is -7. And now I'm done. I have a complex number as my solution, with my real component being -7 and my imaginary component being 24I. And I could graph this. Right? I could take this right over here. -7 plus 24I. -7 would be way out here. 24I would be way up there, even further. And I would draw a ray up to that point. I don't want you guys to graph it, but I could graph this if I had to. We'll start D, and I'll have you guys try to finish D. So D is going to be a little tedious. I have I plus 4x times I plus 4x, and again another I plus 4x, because now we have a complex number that's being cubed. And I will start by foiling, but I'm only going to deal with the first two terms first. I'm going to leave that third I plus 4x alone until I've simplified these two. So I times I is I squared. I times 4x is 4xi. I always put the imaginary component on the end. And then I have another 4xi. And then I have a 4x squared. 4x times 4x. Don't forget, we still are going to eventually multiply this by I plus 4x. And I can start to simplify this, right? I squared, that's just -1. 4xi plus another 4xi is going to be 8xi. And then I have a 16x squared here as well. So I can simplify some of that. I have -1 plus 8xi plus 16x squared. I would rearrange this so that it's in a plus bi form before I distribute again. So I would put my real stuff, that's my real stuff, in front, and I would put my imaginary stuff on the end. Okay. Okay, from here I'm going to distribute one more time. 16x squared times both of these terms, -1 times both of these terms, and 8xi times both of these terms. So here's what I'll end up with. 16x squared I plus 64x to the third minus I minus 4x plus 8xi squared plus 32x squared I. Now what I'd like you guys to try is, before you come in tomorrow, I want you to try simplifying this expression. Substitute anything you can in for any powers of I that you see there that could be simplified. Make sure that you write it so that your real components are in front and then your imaginary components are on the end. You'll have a few of each. You'll have a few real components and a few imaginary components. All right, but try to finish this up, and then tomorrow I'll show you guys what this should look like.